Hello students. So today I want to explain about a second. Okay, okay. So energy bands in materials. So there are three bands and two bands are there. One is valence band, another is conduction band. So valence band is nothing but we can call this as low energy band. So whatever the electrons associated with the atomic structure, so that is present in the valence band. So we can also call as a low energy band. Okay, that means the band associated with valence electrons. Okay, we call as valence band. So as I told you that whatever the electrons, valence electrons are there that are bonded to the atomic structure. So when they are bonded to the atomic structure, they will not participate in any current flow. Okay, so the electrons present in the valence band, they will not participate in any current flow. Okay, that is related to valence band and conduction band. So conduction band is also called as we call as high energy band. So conduction band is associated with free electrons. So that means whatever the free electrons are there, that will be available in conduction band. So these free electrons which are present in conduction band, those are not associated with the atomic structure. Okay, so that means that will come out from the atomic structure and they make free and they will jump from valence band to conduction band. So they will participate in current flow. So whatever the electrons present in the conduction band, so due to that so due to this free electron flow, there is a conduction takes place. If there is a conduction of means if there is a movement of electron, there is a current flow. So that's why the name came conduction band. Okay. And next forbidden energy gap, if you see the distance between valence band and conduction band we call as forbidden energy gap. Okay. So there will be no electron present in the forbidden energy gap. Either electron will be present in valence band or the electron will be present in conduction band. Okay. So if you take the silicon atom, so you see here, all the electrons are associated with the atomic structure. So what is the valency for silicon? 4 is the valency for silicon. And so that means 4 electrons will participate in sharing of this another silicon atom. And it's like a sharing of electrons, like it will form a covalent bond. Okay, form a sharing of electrons is nothing but covalent bond. So that's why we get the silicon atoms in terms of crystal in nature. So many the silicon atoms are bounded in terms of crystal. Okay, so crystalline silicon, we call it a crystalline silicon. So during room temperature, this is acting as insulator. So during 0 Kelvin, it is acting as insulator at room temperature. So at room temperature, what happens? Whatever this electron bonded with the atomic structure, that will acquire some energy, thermal energy. Due to thermal energy, this will break this covalent bond and this makes one free electron. Okay. So from this, we can understand that silicon at 0 Kelvin, it acts as insulator and at room temperature, that is 300 Kelvin, some amount of conduction will take place. So this free electron it will be not free, it will jump from valence band to conduction band and it will take part for the conduction. Okay, so this is about energy band diagram. So if you see the classification of solid materials, those are divided into three types. One is conductor, semiconductor, and insulator. Okay. So this is the energy band diagram. So first we will see the conductor and insulator. So what is the difference between conductor and insulator? So conductor, so example I told you like copper or aluminum or silver, gold. These all are nothing but good conductors. The energy gap is very small. Okay, so that means negligible. It is nearly equal to zero, and so that means that you can say that there is no energy gap, and conductivity is more value around 10 power 7 per ohm meter, and resistivity is high value 10 power minus 7 ohm meter. So we can say that conductivity and resistivity are reciprocal with each other. So sigma equal to, you can write 1 by rho. Okay. So example, copper and aluminum are good conductors. Okay. And next, coming to the insulators, there is more forbidden energy gap. This is between the valence band and conduction band. This is around like 6 electron volt to 15 electron volt. The forbidden energy gap is nothing but 6 electron volt to 15 electron volt. So that means 1 electron volt. This is the energy gap. Okay. So 1 electron volt equal to, you can say that 1.6 into 10 power minus 19 joules. Okay. So that much of energy is required for the electron to jump from valence band to conduction band. Okay. So here, if you say 6 electron volt, 6 into 1.6 into 10 power minus 19 electron volt, that much of energy is required. Okay. To jump from valence band to conduction. So forbidden energy gap is more for the insulator. So if it is more, conductivity is less. Okay. Sigma is less than minus 10 power 10, and sigma resistivity is more. Sigma is more than 10 power 10. Example, mica and wood. These are insulators. We can call as insulators. Whereas semiconductor, whatever our conductivity and resistivity lies between conductor and insulator. Okay. And forbidden energy gap also. Suppose if you take for silicon, the forbidden energy gap is 1.1 electron volt, and for the germanium, it is around like 0.7 electron volt. Okay. So conductivity lies between 10 power 4 to 10 power minus 6 per ohm meter, and resistivity lies between 10 power minus 4 to 10 power 6 ohm meter. So like silicon and germanium, these are uh, semiconductor materials. Okay. If you see the silicon, so valency is 4. Valency of electron. How many valence electrons are 4? Are there 4? And germanium also, you have valence electrons 4. Okay. So so why silicon is widely used means, if you see like electrons are available in the valence shell. In which shell it is available? K shell, L shell, and M shell. In third orbit, 4 electrons are available. And for the germanium, 1, 2, 3, 4, fourth orbit. Okay. So K shell, L shell, M shell, and N shell. Okay. In the fourth orbit, the valence shells are available. So as I told you, as the electrons are moving away from the nucleus, the energy increases, and it is easy to move, or easy to excite this electron from the atomic structure. Okay. So this germanium is more sensitive to, okay, and it is having high reverse current. So that's why we are not using germanium for the semiconductors. So mainly we are using silicon for the semiconductors. Okay. So that is the reason. Reason using silicon over germanium. Why we are using. So, so if you see the atomic structure, the valence electrons of germanium is available in fourth orbit, while as the valence electrons of silicon are available in third orbit, that is close to the nucleus. Okay. So germanium valence electrons at higher energy level, those in silicon. That means small amount of energy is required to remove these valence electrons from the germanium compared to silicon. And one more property, germanium is available with that high temperature, and it is having high reverse current. That's why we are not using germanium. We are using silicon, and so many techniques came to make silicon, and from the silicon itself we can make an insulator, that is silicon dioxide, that we are going to use as a insulator for in the MOSFET. Okay. So that is one more advantage of using silicon over germanium. So energy levels are band of silicon atoms. So if you see, so energy levels, if you, that means, uh, so each energy band is associated with certain amount of energy that is separated by energy bands that you will see. So that means no electron exists in the energy gap. We have two energy levels, no, valence band and conduction band. Okay. So this is energy gap. If you see the silicon, so we are not concentrating on this octet level energies. That means E2 and E1, like next two here, E1 is having 2 electrons, E2 is having 8 electrons. These are already in octet position. So we are only concentrating on the valence band, okay, whatever the valence electrons are there. So how much is the valence band? That is E3 is having 0.7 and E4 is having 1.8. So the 1.8 minus 0.7 means the energy gap of silicon is 1.1 electron volt. Okay, so that is the energy gap of silicon. So same thing whatever I explained. So the energy gap is 1.8 minus 0.7, that is 1.1 electron volt. Okay, so that means whatever these valence electrons are there, whatever the chemical properties and physical properties and electrical properties are depending only on the valence electrons. Okay, so that's why we are concentrating only on the valence electrons. Okay, coming to the semiconductor material, there are two types of materials. One is intrinsic and next one is extrinsic. So intrinsic is nothing but we can call as pure form of semiconductor, and it is having lower conductivity. As I told you, like at 0 Kelvin, it is acting as an insulator. At 300 Kelvin, what happens? It will acquire some energy. This whatever the electron in the bond, it will acquire some energy, and it will break this bond, and one free electron will be formed. So when the one free electron is forming, one free hole will be formed. Okay. So that means we can say that at 0 Kelvin, no free charge carriers are available, and it has number of electrons equal to number of holes. As temperature increases, resistance decreases. So as at 300 Kelvin, the conductivity increases. No? So free electrons are forming, and it is jumping from valence band to conduction band. So that's why as temperature increases, resistance decreases. That's why this intrinsic semiconductor have negative temperature coefficient. Okay, and whereas extrinsic semiconductor, uh, whatever the pure semiconductor, we are making into impure by doping with impurities. We make this as extrinsic semiconductor. So due to impurities like N type and P type. So N type means what? We will dope with pentavalent impurities. What are the pentavalent impurities? Which is having 5 electrons in the valence group, fifth group. Okay. So phosphorus, arsenic, antimony, bismuth. These are the fifth group. So when you are doping, one more electron after making into this pairing of electrons, one free electron is available that is responsible for the conduction in N type. So the majority carriers are electrons and the minority carriers are holes. And here P type, when you are doping the pure semiconductor with trivalent impurities like third group, so after making bonding, one free hole will be formed. Due to that free hole, the current conduction takes place. So we can say that the minority carriers are holes and majority carriers are electrons. Okay. So due to this impurity, whatever the impurity is there, there is higher conductivity. Okay. So impurities will define the number of electrons and number of holes. So how you can define the impurity in terms of what? Part per million. So you know that 1 million equal to how many lakhs? 10 lakhs. Okay. So that means in 10 lakhs silicon atom, we are adding one impurity, one phosphorus atom. We call it one part per million. Okay. We'll get N type. Suppose in 10 lakh silicon atoms, we are adding one boron atom. Okay, we are getting trivalent, means a third T-type semiconductor. Okay, so example N-type and P-type. Okay, so these are the two examples like N-type. So how we are getting N-type is silicon material. We add pentavalent impurity, 5 electrons in the outermost orbit. Okay, so for adding every impurity, here we added one phosphorus atom. So one electron is formed. Okay, so that means for adding every impurity, that many free electrons are added. Suppose if you are adding like 100 phosphorus atoms in this pure semiconductor, 100 free electrons will be formed. Okay, so these are under so pentavalent impurities are from group 5, like phosphorus and antimony. And what are the majority carriers? In N type, electrons are the majority carriers and holes are the minority carriers. Okay, and in P type semiconductor, we add trivalent impurities. Whatever the trivalent impurities, that means which is having 3 electrons in the outermost orbit, we call as trivalent impurities. Okay, so every impurity, one free hole will be formed. So that means here, if you see the diagram, silicon is replaced with the trivalent atom, that is aluminum. So when it is added with aluminum, so what happens? One free electron is formed. So if you are adding like 100 aluminum atoms, 100 free electrons will be formed. Okay. So these impurities are from which group? Third group, like aluminum and boron. So what are the majority carriers? In the p type, holes are the majority carriers and electrons are the minority carriers. Okay. So next. So there are two. So we'll discuss about the currents in the semiconductor. There are two currents are there. One is drift current. Next one is diffusion current. So we'll see first drift. What is drift current? And next we'll see the diffusion current. Okay. So so drift current. So that means before that we'll see the drift velocity. So what is it drift velocity? Suppose pole is moving like this. Okay. Black line is nothing but trajectory without applying external trajectory of hole without applying external electric field. Okay. And this brown line shows that after applying external electric field, this is another hole. Okay. So Vd equal to what? Mu into E. So that means this distance we call as Vd, drift velocity. There is a change in the trajectory before applying external electric field and after applying external electric field. Okay, this is Vd. Vd equal to mu into E, where Vd is nothing but what? Drift velocity, and mu is nothing but mobility of charge carriers, and E is nothing but applied electric field. So Vd equal to mu into E. So for the semiconductor, suppose if you are applying external electric field, okay, external voltage. Due to this external voltage, there is an electric field. Okay, we can say that electric field E equal to what? E equal to minus dV by dx. Okay, so when you apply external electric field, positive to this one. Okay, when you apply positive, whatever the electrons are there, that will be attracted, and whatever the holes are there, that will be repelled. So you know that like electrons are moving from left to right to left. The conventional current is the current will move from right to left. As holes are repelling, that means it is moving from left to right. So the whole current will be same direction. So from the Coulomb's law, we can say that whatever the force, okay, force equal to Q into E. Okay, Q into E. Force is a Q into E. Q is the charge and E is the electric field. So what is drift current? It is due to what? Applying electric field. The current is due to applying electric field. So we can say that I equal to MEAVD. So we are concentrating on the current density. So that means current per unit area is nothing but current density. So J equal to ME into VD. So we already know VD. VD equal to what? VD equal to mu into E. Okay. So that means J equal to ME into mu into E. Okay. So that means here M is nothing but carrier concentration and A is nothing but area of cross section of the material. And Jn is nothing but what? Drift current in N-type material. That is equal to MQ mu N into E. Mu is nothing but mobility. Okay. And drift current in P-type material is PQ mu P into E. Okay. So where J and JP are the current density due to holes and electrons. And mu N and mu P are nothing but mobility of electrons and holes. So what is the total current density? So we can write NQ mu N into E plus PQ mu P into E. So if you take common N mu N plus P mu Q into E. So we can consider this as sigma. Sigma is nothing but conductivity of material. So that means sigma equal to what? N mu N plus P mu P into Q. So we can write the drift current equal to sigma into E. By applying external electric field, you will get which current? Drift current. Okay. Next, diffusion current. So what is diffusion current? Diffusion current is due to what? Concentration gradient in the material. Okay. See here, if you take like P-type semiconductor, the concentration of electrons is more here, and concentration of electrons is less here. Okay. So if you draw the charge carrier concentration with respect to distance, the concentration is more here. Okay, and concentration is less here. Okay. So from this you can say that diffusion current equal to what? Jn equal to q dn by dx. Dn by dx is nothing but what? Concentration gradient. And diffusion current is due to what? Holes. So Jp equal to minus q dt into dt by dx. So why minus? As electrons are flowing from left to right, the holes will flow from right to left. The whole current direction will be opposite to the direction of electrons. Okay. And dn by dx and dt by dx are nothing but concentration gradient. And dn and dt are nothing but diffusion coefficients of electrons and holes. Okay. So what is total current density of semiconductor material? So we can write as drift current density plus diffusion current density. Okay. So in an N-type semiconductor, total current equal to what? Nq mu n into E plus Q dn by dx. For P-type material, Nq mu P into E minus Q into dP into dn by dx. Okay. And next we will see the mass action law. So what is mass action law? It is the product of electron concentration and hole concentration, that is equal to what? Intrinsic square of the intrinsic concentration. Okay. Np equal to Ni square, and N is number of electrons and P is holes, hole concentration, and Ni is nothing but intrinsic concentration. So as I said, like you need to prove the mass action law. As I said, at 0 Kelvin, silicon, whatever the silicon is there, it is acting as insulator. Okay. There is no free electrons. Okay. At room temperature, what happens? Whatever the this electron is there, this electron will acquire some energy, thermal energy. Due to thermal energy, this will break this covalent bond and this makes this free electron. Okay. So due to this free electron, so I can say that electron will be generated and it is jumping from what? Valence band to conduction band. So when it is generating, suppose some more electrons or free electrons are available, that will come and that will recombine in this hole. Okay. So from this we can say that generation in conduction band. Okay. Generation that is in the conduction band, that is equal to recombination in the valence band. So generate, we can say that generation equal to recombination. Okay. So from this we can say that, so in intrinsic pure semiconductor, so number of electrons equal to number of holes equal to intrinsic concentration. So that is N equal to P equal to Ni. Okay, for intrinsic semiconductor. These are the fixed values you need to remember. So Ni equal to, for silicon, Ni equal to 1.5 into 10 power minus 10 per centimeter cube. And for germanium, Ni equal to 2.4 into 10 power 10 per centimeter cube. As I told you, generation equal to recombination. So generation is directly proportional to what? Ni square, and recombination is directly proportional to Np. So if you take the proportionality constant, you will get the proportionality constant R. R equal to Ni square, R equal to Np. So if you substitute R into Ni square equal to R into Np, Ni square equal to Np. So you are getting mass action. Okay. For N-type semiconductor, if you take the majority carriers as electrons and minority carriers are holes, you are getting N equal to Ni square by P. Okay. And for P-type semiconductor, majority carriers are holes and minority carriers are electrons. You can write P equal to Ni square by N. Okay. Okay. So this is about mass action law. Okay. So till here, I think you understood. So what we discussed, from starting. So what is like you see classification of solids? Okay, classification solids. Okay, energy bands in materials, classification of solids, and why silicon is preferred over the germanium. Okay, energy bands in silicon. Okay, and seen the different types of materials, means in semiconductor materials, intrinsic and extrinsic. Again, extrinsic, N-type and P-type. N-type and what are N-type semiconductors and what are P-type semiconductors? And before drift current, we have seen the drift velocity. What is drift velocity? And we have seen the Coulomb's law, if equal to Q into E. And what is drift current we have seen, and what is conductivity we have seen, and what is diffusion current we have seen. Drift current is due to what? Drift current is due to electric field. Okay. And diffusion current is due to concentration gradient. Okay. And next, we have seen the mass action law and proof for mass action law. So I think you understood. So thank you for this video.